Okay, so continuing from the previous lecture, our statistics in AI, then we have dimensionality reduction techniques to reduce the number of features while preserving important information. We are going to reduce the number of features while preserving important information. Principal component analysis reduces the dimensions by finding principal components that explain variance. Then singular value decomposition, matrix factorization method used in text and recommendation systems. TSNE, T distributed stochastic neighbor embedding, visualizes high dimensional data by reducing it to 2D or 3D. Factor analysis, it explains observed variables using a smaller number of latent factors. Now comes time series analysis. It analyzes data indexed in time order. ARIMA autoregressive integrated moving average combines autoregression and moving average for time series forecasting. Exponential smoothing weights recent data more heavily for forecasting. Hidden Markov models models sequences with underlying hidden states. Seasonal decomposition of time series separate time series into trend, seasonality, and residuals. Now, Bayesian statistics and probabilistic models framework for reasoning under uncertainty. Bayesian networks, graphical models representing probabilistic relationships. Markov chain Monte Carlo, sampling based method for Bayesian inference. Expectation maximization is an iterative algorithm to find maximum likelihood estimates for models with latent variables. To find maximum likelihood estimates for models with latent variables. Dirichlet processes, non-parametric Bayesian methods for clustering. Now comes optimization techniques, statistical methods for model training and parameter estimation. So maximum likelihood estimation MLE estimates parameters that maximize the likelihood of the observed data. Likelihood of the observed maximizes. Gradient descent optimizes loss functions by iteratively updating parameters. Optimizes loss functions by iteratively updating parameters. Stochastic gradient descent, variant of gradient descent using small random batches of data. Conjugate gradient descent and Newton's methods, advanced optimization methods for faster convergence. Then resampling methods. Then resampling methods, techniques to improve model performance and evaluate uncertainty. Bootstrap, random sampling with replacement. Random sampling with replacement to estimate statistics and confidence intervals. Cross validation, Splits data into training and validation sets for model evaluation. Splits data into training and validation sets for model evaluation. Jackknife removes one observation at a time to estimate bias and variance. So removes a one observation at a time to estimate bias and variance. Now decision trees and ensemble methods. Methods for classification and regression. Decision trees and ensemble methods. Decision trees splits data based on feature thresholds. Random forests combines multiple decision trees for better accuracy. Gradient boosting machines sequentially combines weak learners to correct errors. AdaBoost adjusts weights of weak learners to focus on hard to classify examples. Adjust weights of weak learners to focus on hard to classify examples. To focus on hard to classify examples. XGBoost and Light GBM, scalable and efficient implementation of gradient boosting. Then come graphical models used for structured data and probabilistic reasoning, Markov random fields, models relationships between variables in a graph. Conditional random fields, sequence modeling with structured predictions. So, sequence modeling, structured predictions. Bayesian networks, directed acyclic graphs representing probabilistic relationships. Then Monte Carlo methods. Simulation based methods for probabilistic modeling. Monte Carlo integration. Estimate integrals using random sampling. Markov chain Monte Carlo generates samples from complex distributions. Importance sampling focuses on important regions of the probability distribution. Important sampling is it focuses on important regions of the probability distribution. Now, statistical learning theory. Theoretical foundations for machine learning. Uh, Bias variance trade off, balancing underfitting and overfitting. Pack learning, probably approximately correct learning. Framework for understanding learnability. It's interesting. VC dimension measures model complexity and capacity. So, by combining these statistical methods, AI systems can analyze data, recognize patterns, make predictions, and adapt to a new information. Adapt to the choice of method depends on the problem, data characteristics, and computational requirements.